Okay, so as I was saying, so if we integrate this stress over this area, we'll get an equivalent force, F equivalent here. We get another F equivalent over here. And hopefully it's obvious that these two guys together, they're going to create something, a torque that's going to act to rotate this beam. And since we know it's in equilibrium, well, it turns out that there has to be a moment, that basically a bending moment that acts against this. So there has to be some bending moment. So this is a torque, we label it as M, a bending moment, that opposes the torque from these equivalent forces to keep the thing at equilibrium, so it's not rotating. Okay, and so just from looking at this, from the way that we I gave you an argument why intuitively this is the case. So now we can write out the math, right? So we've got M is equal to, the bending moment is equal to the integral of the stress from minus h over 2 to h over 2. And the key idea here is we've got basically sigma x as at a point y, and it's going to be multiplied by the moment arm, y, okay? And then we have to multiply by w, which is the width into the page. So this stress distribution is the same as we go into the page here, and so we multiply by w. And then we're going to integrate that whole thing over dy, okay? And so this is a pretty easy integral. The thing that we need to know is that if we look back at the, well, actually, we could even write it, if we look back at the previous page, well, we had that this is the dependence of the strain on y, okay? So we could write that, again, that graph, we can express it in terms of an equation. So we could write that the x-axis strain as a function of y is equal to epsilon x max times y divided by h over 2, right? So when y is equal to h over 2, we get epsilon x max, and y equals minus h over 2, we get minus epsilon x max, and it's sort of linear in between those 2 points. Okay, so that's what we know. And then, well, we have an equation that's in terms of the stress, right? And so we're going to use this stress-strain relationship. Okay, so we're going to rewrite this as m is equal to the integral from minus h over 2 of e times epsilon x of y times y w dy. And then I'm going to substitute in for my expression for the strain. And so I'm going to start pulling variables out of the integration. So we've got e, right, the Young's modulus doesn't depend on y. And we have epsilon x max here. And we can pull out h over 2. Actually, we can pull out w too. And then we get the integral from minus h over 2 to plus h over 2. And from this guy, I got a y, and I already had a y. So I get y squared dy. Okay, so all I did was I substituted this expression for the strain into this integral for the moment, and this is what I end up with. Okay, so this is the final equation that I have. And where did this all come from? Well, it came from the idea that what I'm doing is I integrated the stress over this surface from minus h over 2 to plus h over 2, and I know that that integrated stress times the moment arm, right? So I've got at each point I'm calculating the stress at that point, and I'm multiplying by its moment arm, and so that's what's equal to this bending moment here on the left-hand side. Okay, so that's where all that stuff came from. And now, like I said, this is a pretty simple integral, so I will take a little bit more space, and we get all the stuff that's in front still stays there. I might move that factor of 2 up just to sort of make it a little bit more clean. So we have 2e epsilon x max divided by h, whole thing times w, and I end up with y cubed over 3, so not very hard. And I could substitute in the limits of integration, right? So this is h over 2 here, and then minus h over 2. Okay? And when I plug all that stuff in, what I end up with is that m is equal to 1/6 e w h squared times ex max. Okay. So now I have an expression that relates the bending moment to the maximum strain. And the other parameters are in here. Well, there's the Young's modulus, then there's the width and the height of the beam. And now what I need to do is I need to use a little bit more geometry to carry this further. So it turns out that the bending strain is related to the curvature of the beam by geometry. And if we look at this segment here, well, so here is r is the radius of curvature of the beam, and so this little segment, this arc length here, well, this is obviously r d theta, okay, and well, what is the length of this arc segment up here? Well, it's r plus h over 2 d theta, right? So the length to the radius from the radius of curvature to the neutral axis here, that gives us r d theta, and then we've moved an additional h over 2, half the beam thickness, and so now this is the arc length. And what we know is that epsilon x max is basically the strain at the top surface of the beam. And the definition of strain, the way we usually write this is that we write it as delta L over L. It's the change in length divided by the original unstrained length. And in the context of this particular problem, well, the unstrained length here is this r d theta. And, well, this length here is the total strained length. So delta L is just a change in length. And so what we could do is we could write that epsilon x max is equal to r plus h over 2 d theta minus the unstrained length, r d theta, whole thing divided by the unstrained length, r d theta. Okay, and well, we had a d theta in there, but that actually drops out because it's in the numerator and the denominator, and so it sort of cancels. And what we're left with is that epsilon x max is equal to h over 2r. Okay, that's the maximum strain. And you might ask yourself, well, this is the what do I do with this? Well, it turns out from basic calculus that we know that we think of the slope as being equal to dy dx, and it turns out that the curvature is d squared y dx squared, okay? And so this is the curvature, and so that's equal to 1 over r, okay? 1 over r. So here we have this equation where we can see that epsilon x max is related to 1 over r, and so we can use that. Let me give myself a little bit more room. We could write that epsilon x max is equal to h over 2 times d squared y dx squared, okay? And how are we going to use this? Well, we have a relationship that relates the bending moment to the strain, and now we have a relationship between the strain and the curvature. And so what we can do is we can connect these two things together. I'm going to look at the previous, I have to cheat a little bit and look back at what the previous one says. So it said m is equal to 1/6 e wh squared times epsilon x max. I'm going to substitute that in, h over 2 d squared y dx squared. Okay, and so now we're going to get a relationship between the bending moment and the curvature of the beam. And we can write this in a more simplified fashion. M is equal to 1/12. I'm going to write it like this, sorry. Write it as E W H cubed over 12 times d squared y dx squared. Okay? And so this is basically pretty much where we want to be. This is the pretty fundamental equation for us. It relates the bending moment to the curvature of the beam. And we have all this other funny stuff in here. Well, Young's modulus is not very funny. We know about that thing. But this parameter in here, actually these geometrical parameters, it turns out they have a name. Oops, I guess I didn't need this line, so I'm going to skip it. Okay, so, aha, moment of inertia. Okay, and it says already here, the term WH cubed over 12 is defined as the moment of inertia, IZ. Okay, and, well, where does the Z come from? So if you remember our beam, we've got X, Y, and here's Z. So we're talking about basically rotations about the z-axis, right? Because the z-axis is coming out of the page. And so as we bend this thing, we're really thinking about the rotation of the beam about the z-axis. And so IZ is WH cubed over 12. And so what we could do is we could rewrite our equation as M is equal to EI times d squared y dx squared. And this is the fundamental equation that you will often see. And really you could think about this M, this bending moment, is also a z-axis bending moment, right? It's a torque about the z-axis. Okay, so like it says here, large moment of inertia means low curvature, small deflections, and stiff. So, you know, you may know about moment of inertia like in terms of a rotating body, right? So this is the area moment of inertia, right? So the real moment of inertia of an object is basically some kilogram meter squared. It turns out this is the area moment of inertia, is what we're really calling this IZ. And it says here, okay, design implications. Rigidity increases as the cube of the beam's thickness in the direction of bending, and the aspect ratio H over W determines the ratio of the bending rigidity in the Y and Z directions. So if you think about like this sort of structure, let's imagine that that we're talking about. So now I'm looking at the cross section of the beam, and I'm kind of uncomfortable with drawing it like this. So I'm looking at the cross section of the beam. So this is still the y-axis here. So now this is the z-axis, and sort of the x-axis is pointing out towards us. Okay, so this is a cross section. Right, and so if we label the dimensions on here, this was the dimension that was into the page before, right? Because z was the dimension that was coming out of the page. So now we've cut it. This is W. This is H here, right? This is H and W. So here W is equal to H. Here is one that is much taller than it is wide. And so if you think about, well, what does this mean? So we said that that the IZ is WH cubed over 12. So similarly, you could, hopefully I can convince you without really talking about it a lot, that the y-axis moment of inertia is equal to HW cubed over 12, right? And so that's, if we were to imagine, for example, this is a y-axis force here, right? We were talking about bending it, and that would be, I need a little bit more space here. So Fy for bending, we're going to use Iz, and if we have a force in the z-axis, we're going to use Iy. And so this particular beam is basically very flexible in the for forces in the y-axis, it's very stiff for forces in the z-axis. And this one is just the opposite, because it's the same beam and I'm rotated it the other way.